2015 question 9. First part says, part A, define an acid according to Arrhenius. Okay, so again, an Arrhenius acid is one that dissociates in aqueous solution to produce H plus ions. Okay, that's my definition for an Arrhenius acid. Second part asks me, define a Bronsted-Lowry acid. So a Bronsted-Lowry acid is a proton donor. A good proton donor would be a strong one. Okay, part B says define pH. pH is minus the log of the H plus ion concentration. State one limitation to the pH scale. Limitations, we've got a couple of them. It's not reliable in solutions greater than 1 molar. It only applies in aqueous solution. And I could also say that, of course, it's only reliable at 25 degrees Celsius. But I'm only asked for one anyway. So now the next part, you have a table given to you with volumes of NaOH added to an ethanoic acid solution, and you're given the pH and you have to draw a graph. So you end up with this kind of thing. Obviously you do it on graph paper, girls. I haven't done it on graph paper, but I should do it on graph paper. Be very, very careful when you're plotting the vertical part. They gave you a lot of points to plot at the end point, so be really, really careful there. Label your axis pH for the y-axis and label the x-axis the volume of NaOH in centimetres cubed. So first part you graph that titration. Now this next part says calculate the initial concentration of ethanoic acid in the beaker. So the initial concentration of ethanoic acid, let's have a look. How will I get that from this information? So the initial concentration of the ethanoic acid, again a weak acid, well, I know that the pH of a weak acid is minus the log of the square root of Ka by molarity. So what they're asking me is for the molarity. I know what the pH is. I read it from my graph, the first point on my graph is 3.3. So this is 3.3 is equal to minus the log of the square root of. The Ka is given to me in the question. It says the ethanoic acid has a Ka of 1.8 by 10 to the minus 5. So I'm going to multiply that by the molarity. I'll get the anti-log of minus 3.3, and that will give me 5.012 by 10 to the minus 4. That will be equal to the square root of 1.8 by 10 to the minus 5 multiplied by molarity. So I'll square the 5 by 10 to the minus 4 and I'll divide it by the 1.8 by 10 to the minus 5. And my final answer then, when I do that, that will release the molarity from the square root and I should get 0.014. So that's the molarity. Now it says make use of your graph to deduce the volume of sodium hydroxide solution required for neutralization. So I'm going to go back to my graph. I'm going to have a look to see where the vertical part is. So here's the vertical part. And I'm going to read off the amount of sodium hydroxide that was needed for neutralization. So for the second part of that question, the volume of NaOH, according to me, is about 22 centimetres cubed for neutralization. Okay, and then there's one more part. What indicator could be used to detect the end point of the titration? Okay, what indicator would I use? So I'm looking here. I know it's a weak acid, strong base. So I'm just going to move the graph out the way and write that here. So a weak acid versus a strong base titration. I know what kind of the indicator I would use for that. I'd use phenolphthalein. Now, why would I use phenolphthalein? Of course, you have to justify your answer and refer to your pH curve to justify your answer. Okay, it's a weak acid strong base titration, and I'd use phenolphthalein indicator since it changes colour. The indicator will change colour between a pH range of 8 to 10, and this, which coincides with the end point of the titration. So the end point of the titration is where the vertical part of the graph is. So this is the vertical part of the graph. And we'll just bring that back again. Look at the graph. Now the vertical part of the graph is here. And look where the change is. It starts at around 7, just over 7, about 8, about there. So it starts, like the vertical part is about there, and then it finishes off about here. So again, that's between 8 and 11.5. So the vertical part of the graph is from pH 8 to about 11.5, and that coincides with the phenolphthalein colour change.